Hey there, physics explorers. Ever wondered how your phone charger turns that alternating current from the power socket into the sweet, steady direct current your gadgets crave? Well, say hello to the half-wave rectifier, the humble bouncer of electric circuits who only lets in the good vibes, or rather, the positive half of an AC wave. Here's how it works. In a half-wave rectifier circuit, we use a single PN junction diode connected in series with a load resistor. It's like setting up a picket fence the current can't climb over during the negative half of the wave. The setup is simple. We hook up an AC voltage source to a diode, which is then connected to a resistive load. Now, this clever diode only allows electric current to pass when it is forward biased, that is, during the positive half cycle of the input AC. During the negative cycle, the diode is reverse biased and acts like a no-entry sign, blocking current completely. So, if you were to look at the output voltage across the load over time, you'd find it matches the positive half sign of the AC input. That is, V out as a function of time equals Vm multiplied by sine of omega t, but only for values of omega t between 0 and pi radians. During the other half, it's flatline 0. Now, while this method does give us DC-like current, don't expect it to win any efficiency awards. The theoretical max efficiency is only around 40.6%, and the output is full of ripples, those wavy voltage swings caused by current being available only half the time. Alright, we've got the circuit, but what does the output actually look like? Imagine a sine wave that got a haircut on one side. That's the result from a half-wave rectifier. The output waveform only includes the positive half cycles of the original sine wave. Every time the input goes negative, the diode goes on vacation, zero output. That's how we end up with a series of voltage bumps and flat lines. Important detail here, since we are only taking in every other half cycle, the ripple frequency, the frequency of the output ripple, is the same as that of the input AC. In other words, ripple frequency equals FAC. To understand the effectiveness of this conversion, we calculate a few output stats. First, the average or D to C value of the output voltage. It comes out to VDC equals Vm divided by pi, where Vm is the peak voltage and pi is approximately 3.14. Next, we look at the root mean square, or RMS, value of the output, sort of like the average power capability. For a half-wave rectifier, VRMS equals Vm divided by 2. This tells us that although power flows, we are losing quite a bit of it compared to the full alternating input. In the waveform diagram, picture a sine wave where only the upper half arches survive. The lower ones? Wiped out. That's the hallmark of half-wave rectification. Now, let's crank up the efficiency. Meet the full-wave bridge rectifier, the superhero team of 4 diodes that tame both halves of the AC wave. While the half-wave version just shrugs off the negative side, this setup transforms both sides into usable output. Here's the trick. The circuit uses 4 diodes, arranged in a bridge so that the current flows through the load in the same direction during both halves of each AC cycle. On the positive half cycle, 2 of the diodes conduct and steer current one way. On the negative half cycle, the other 2 diodes take over and continue the flow in the same direction across the load. Genius! The result? Instead of getting 1 voltage bump per cycle, now you get 2. The output voltage becomes the absolute value of Vm multiplied by sine of omega t. That means all the voltage humps now point upwards, no more zero flatlining. Even better, the ripple frequency doubles. If the input A to C frequency is F, then the output ripple frequency is 2 times f. That makes the output easier to smooth and boosts efficiency significantly compared to the half-wave version. In the diagram, picture a full bridge where all 4 diodes, D1 through D4, create alternate conduction paths for each AC direction. The current arrows zigzag cleverly but always pass through the same load resistor RL in a single direction. Now that a full wave bridge is up and running, what does the output look like? Think of a bouncing sine wave that never turns negative, each bump flipped vertically so every cycle keeps the voltage in the positive zone. The waveform includes all the original AC cycles, but thanks to our diode wizardry, they're now fully upright. The logic of diode conduction ensures both halves are put to work, not wasted. So what's the reward for all this cleverness? A boosted average output voltage. Specifically, VDC equals 2 times Vm divided by pi. That's double the average voltage of a half-wave rectifier for the same input peak. If you're checking the RMS value, the root mean square output voltage, it's Vm divided by the square root of 2. That's the same as the A to C input's RMS value if we assume ideal diodes with no voltage drops. And because we are now flipping both halves of the input, the ripple frequency gets doubled to twice the frequency of the AC source. That's great news if you want smoother D to C, since a higher frequency ripple is easier to filter out. On the graph, you'd see the original sinusoidal wave and next to it a fully rectified version with only upward humps, like a sine wave doing a bunch of push-ups on one arm. Now, the rectifier gets the job halfway done. But if you want truly smooth, stable D to C, you need to send that bumpy output to the electrical equivalent of a SPA, a filter circuit. Most common is adding a capacitor across the load. Here's what happens. During the rising edge of each voltage bump, the capacitor charges up quickly. Then, as the voltage begins to drop, the capacitor discharges slowly, supplying current to the load and filling in the valleys between the peaks. The result? A much smoother output with smaller ripples. That ripple voltage, by the way, is given by V ripple equals I divided by F times C, where I is the load current in amperes, F is the ripple frequency in hertz, and C is the capacitance in farads. So, the bigger the capacitance, or the higher our ripple frequency, the quieter and smoother the ride. The capacitor acts like a savings account. It stores electrical charge and offers it up when the income, current, stops, smoothing out those harsh financial or electrical dips. The diagram shows a full-wave rectifier feeding into a capacitive filter placed across resistor RL. The output waveform has gone from spiky to silky, a fine example of simple engineering improving usability for any DC-powered device. Let's put the formulas into action with a quick example. Suppose we have a full-wave rectifier with an A to C input that has a peak voltage of 10 volts. What's the average D to C output voltage? We use our derived formula VDC equals 2 times Vm divided by pi. So plug in Vm as 10 volts, we get VDC equals 2 times 10 divided by pi, which equals 20 divided by 3.1416. Do the math, and the average D to C voltage comes out to approximately 6.37 volts. Yep, that's the beauty of full wave rectification. You're getting more out of each wave cycle. And this 6.37 volt D to C is consistent with what we'd expect from a full wave rectifier handling a 10 volt peak sine input. Alright, let's tie this all together. Whether it's a half wave or a full wave rectifier, the main job of the junction diode is to allow current in only one direction, turning unpredictable A to C into useful D to C. In a half wave rectifier, the average or D to C voltage output is Vm divided by pi, and its RMS voltage is Vm divided by 2. For a full wave setup, the D to C output becomes 2 times Vm divided by pi, and the RMS voltage is Vm divided by the square root of 2. Ripple frequency also changes. With half wave it matches the input, that's F. But with full wave rectification, it doubles to 2F. Want smoother D to C? Add a filter. For capacitive filtering, the ripple voltage is I divided by F times C, where I is current, F is frequency, and C is capacitance. Remember, half-wave rectifiers use just one diode and let through only half the action. Full-wave rectifiers, either with a center tap or in bridge configuration, put all parts of the A to C cycle to work. With the help of filters, we turn that pulsating output into a steady, usable voltage, just the kind your phone or computer needs to function properly. And that's a wrap for today. Rectifiers are everywhere, from power adapters to your favorite gadgets. Diodes don't just block, they direct energy in all the right ways. See you in the next session, and as always, keep the current flowing and your curiosity glowing.